Okay, in today's lecture we're going to cover the first part of our section 4.6 material on the rank of a matrix. So let's start by introducing a little bit of terminology. So if we're considering a matrix A, which is an m by n matrix, then each row of that matrix has n entries, and can therefore be identified with a vector in Rn. In particular, an n-dimensional row vector. Now, the set of all linear combinations of the row vectors of a matrix is called the row space of that matrix A, and is denoted by row of A, or the row space of A. Now, each row of this matrix has n entries. So the row space of A can be considered as a subspace of Rn. And since the rows of a matrix A could be identified with the columns of a transpose, we could also think about replacing the row space of A as the column space of a transpose. So let's consider a simple example just to illustrate what exactly the row space of a matrix is. So here we're given a 4x5 matrix A, and we're asked to find the row space of this matrix. So let's give each of these four rows of our matrix a name. So maybe we'll say the vector R1 will be the 5-dimensional vector whose entries are the first row of A. That is the vector 2, -1, 1, -6, 8. Row 2, or R2, would be the vector 1, -2, -4, 3, -2. Our third row vector, R3, is -7, 8, 10, 3, and -10. And our fourth row vector, R4, is the vector 4, -5, -7, 0, 4. So when we're referring to the row space of this matrix A, it would be the set which is spanned by these four rows. That is the set of all linear combinations of those row vectors. So the row space of A could be defined as the spanning set of these row vectors R1 through R4. All right. So here would be a way to identify our row space. So somewhat similar to finding the column space for a matrix, but instead we're working with row vectors. Now, for this example, if we knew some linear dependence relations among the rows of this matrix A, then we could make use of the spanning set theorem to shrink that spanning set down to a basis. So recall that a basis is a spanning set of vectors which are all linearly independent, or a minimal spanning set for our space. So here we don't happen to know any linear dependence relations among these four row vectors. It's not clear whether one is a scalar multiple of the three others. And we could try to make use of row operations on this matrix to identify linear dependence relations. However, row operations on a matrix will not give us that information, because recall, row operations would change the row dependence relations. If we say replace one row by the sum of that row and a scalar multiple of the other. So it might seem like row reducing a matrix is not a valid approach to identify the row space, or a basis for the row space. However, we'll see that row reducing this matrix A is worthwhile, and we'll see why when we take a look at this next theorem. So our next theorem, theorem 4.13 from your textbook, says if two matrices A and B are row equivalent, then their row spaces are the same. And if B happens to be in echelon form, so if we could maybe reduce a matrix A down to its echelon form B, then the non-zero rows of that matrix B form a basis for the row space of A, as well as for that of B. So, and if we were interested in finding the base or a basis for the row space of a matrix, we could row reduce our matrix down to echelon form and take the non-zero rows of our matrix in echelon form as our basis vectors. So let's consider an example making use of this new theorem. Throughout the remainder of this section, we're going to be considering information about our new row space of a matrix, the column space of a matrix, and its null space. And we're going to see how these spaces associated with a matrix are related to one another, and see some properties of these. And in this next example, we can see how if we perform one sequence of row operations on a matrix A, then we can get a basis for all three of these subspaces. So let's consider the following. Let's suppose that we have a matrix A, shown here, and by performing row reduction on this matrix, we can see that it is row equivalent to the given matrix B, which is expressed in echelon form here. Now we're asked to determine, so let's say find a set of bases for the row space of A, the column space of A, and the null space of A. All right. So by our new theorem, theorem 4.13, we have the non-zero rows of the row-reduced matrix B would be a set of basis vectors for the row space of our matrix A. So let's start by saying the following. By theorem 4.13, a basis for the row space of A would be the set of vectors, I'm going to call it B1, which would be the first two, or the non-zero row vectors of the matrix B, which are our first two row vectors. So our first row vector for the matrix B is 1, -2, -4, 3, -2. And the second row is 0, 3, 9, -12, 12. So our new theorem says, well, if we can row reduce the matrix A to this matrix B, then the non-zero rows of B, or those row vectors, would form a basis for the row space of A. So we get that immediately by looking at our matrix in echelon form. So let's consider another example. Here, or the next part of this example, where we're asked for a basis for the column space of A. So recall that in our earlier chapter 4 material, we saw we had a theorem which said a basis for the column space of a matrix A would be the columns of A, which correspond to pivot columns in the row-reduced matrix B. So by looking at the form of our matrix B here, we see that it has two pivot columns, namely the first two columns of B are pivot columns, and therefore the first two columns of the matrix A would form a basis for the column space of A. That result was theorem 4.6 from chapter 4. So we can say, making use of that theorem, a basis for our column space of A is the set of vectors, I'll call it B2, consisting of the first two columns of the matrix A. Those are the pivot columns. 2, 1, negative 7, 4, and negative 1, negative 2, 8, negative 5. All right. So the last part of this problem is to find a basis for the null space of A. So recall from our earlier chapter 4 work, in order to find a basis for the null space of a matrix A, we need to look for the solution set of the homogeneous linear system defined by AX equals to 0. But recall that this would have the same solution set, so that equation is equivalent to the equation Bx equals to 0, where we're using the row-reduced matrix B. So here, considering that system as an augmented matrix, we would have the following. Our first row of the matrix B is 1, negative 2, negative 4, 3, negative 2. Our second row is 0, 3, 9, negative 12, positive 12. And then our last two rows are rows of zeros. Then we're augmenting this with the 0 vector, since we are considering a homogeneous linear system. So let's perform a row reduction on this matrix to put it in reduced row echelon form. So here B was only in its echelon form, not reduced, so that we can find our solution set. So my first column of this coefficient matrix B is exactly as I want. I have a leading entry of 1 in the first row with zeros everywhere below it. And then in my second row, I have a leading entry of 3, which I'd like to be a 1. And I notice that each entry in the second row is a multiple of 3. So to get a leading 1 in that second row, I could simply take 1/3 of that second row. So I have 1, negative 2, negative 4, 3, negative 2, and my second row becomes 0, 1, 3, negative 4, positive 4. And then my last two rows are still rows of zeros. And since this is a homogeneous system, any operation, row operation that I perform on that 0 vector on the right-hand side will still give me the 0 vector. So now I can make use of the leading 1 in my second row to eliminate the negative 2 that appears in the column above it by taking row 1 and adding 2 times row 2. So this makes my first row 1. I would have 2 minus 2 is 0. 6 minus 4 is 2. Negative 8 plus 3 would be negative 5. And 8 minus 2 is 6. Performing the same operation on the right-hand side, I have 0. My second row is now 0, 1, 3, negative 4, positive 4, 0. And then my last two rows remain all zeros. So now my matrix is in reduced row echelon form. We see that we only have 2 pivot columns, so the variables corresponding to columns 3, 4, and 5 are all free variables. So our solution set here could be written in the form x equals x1, which using the first row of our augmented matrix, we can see is equal to negative 2x3 plus 5x4 minus 6x5, and x2, using the second row of our augmented matrix, we can see is equal to negative 3x3 plus 4x4 minus 4x5, and then x3, x4, and x5 are free variables. So rewriting this solution set as a linear combination of vectors where these free variables are the weights, we have the following. X is equal to x3 times the vector negative 2, negative 3, 1, 0, 0, plus x4 times the vector 5, 4, 0, 1, 0, plus x5 times the vector negative 6, negative 4, 0, 0, 1. So these 3 vectors, which we have here, are a basis for our null space. So if we call those vectors, let's say v1, v2, and v3, a basis for the null space. So let's say a basis for null A is the set, let's call it v3, consisting of these 3 vectors, v1, v2, and v3. All right. So this example illustrating how a single row operation or a single set of row operations on a matrix A, bringing it to reduced row echelon form, would allow us to determine a basis for the row space, the column space, and the null space of that matrix. All right. Now, the next part of our section is going to deal with a result known as the Rank Theorem, or in other textbooks, you'll see this called the Rank Nullity Theorem. So this result is going to describe a relationship among the dimensions of the column space of a matrix, the row space of a matrix, and the null space of a matrix. So let's introduce a little terminology that's needed before we can state this theorem. So we will define the rank of a matrix A as the dimension of the column space of that matrix. So here we could say that rank of a matrix A is equivalent to the dimension of the column space of that matrix A. Now, another way to think about this would be as follows. Since the row space of a matrix A is the same as the column space of A transpose, then the dimension of the row space of A is the rank of A transpose. Now, this dimension of the null space of a matrix is sometimes referred to as the nullity of that matrix. So when we're talking about the nullity of a matrix, we're talking about the dimension of its null space. Now in this textbook that we're using for the course, they don't use the term nullity, except in this case to define it. But in other texts, you'll see a nullity used instead of the dimension of the null space of a matrix. So this new terminology allows us to state the rank theorem, or the rank nullity theorem, which is theorem 4.14 from your textbook. So again, in your text, it's called the rank theorem, or sometimes known as the rank nullity theorem. And here's what our theorem says. The dimensions of the column space and the row space of an m by n matrix A are equal to each other. That is, the dimension of the row and column space must be the same. So this common dimension, which we refer to as the rank of A, is equal to the number of pivot positions in the matrix A, and satisfies the following equation. The rank of a matrix A plus its nullity, that is the dimension of the null space of that matrix, is equal to n, the number of columns in our matrix. Recall this was an m by n matrix. So the sum of the rank and the nullity has to equal the number of columns of our matrix. So let's see if we can justify this result. So for our proof here, let's start by saying by theorem 4.6, the rank of a matrix A is, that is the dimension of the column space of A, is the number of pivot positions or pivot columns in our matrix A. So recall that theorem 4.6 said that a basis for our column space would be the pivot columns of our matrix. So therefore the rank of A, which is the dimension of the column space, is the number of those pivot columns. Now equivalently, we can say the rank of a matrix A is the number of pivot columns in an echelon form. Let's call the echelon form of our matrix B of our matrix A. Now, moreover, we can say that since the echelon form B has a non-zero row for each pivot, and these rows form a basis for the row space of A, the rank of a matrix A must be equal to the dimension of the row space of A. That is, the dimension of the column space must be the same as the dimension of the row space. Now recall that the dimension of the null space of a matrix A is equal to the number of free variables in the equation A times a vector x is equal to the 0 vector. So recall the null space is the set of all vectors x, which are mapped by the matrix A onto the 0 vector. And for an explicit description of the null space, we can solve this homogeneous system. And as we saw in our previous example, the number of free variables determines the number of vectors in a basis for the null space, and therefore the dimension of our null space, or the nullity of our matrix. So that is the dimension of the null space of A, or the nullity of a matrix, is the number of non-pivot columns, or number of columns of the matrix A that are not pivot columns. Therefore, we can say clearly the number of pivot columns plus the number of non-pivot columns must be equal to the number of columns. And from what we've already established, the number of pivot columns we know is the dimension of the column space of our matrix, or the rank of that matrix A, plus the number of non-pivot columns we said is the dimension of the null space of the matrix A, or its nullity, and this has to equal the number of columns of our matrix, which we were saying is an m by n matrix, so here equal to n columns. So we've established this rank nullity theorem. So let's take a look at some applications of this rank theorem, or the rank nullity theorem. So in our next example, we have a matrix A, and we can show through row operations that it is equivalent to the matrix B, which is written here in echelon form. And we're asked to, without calculation, list the rank of our matrix A, the dimension of the null space of A, so that is its nullity, and then find bases for the column space, the row space, and the null space of A. All right. Now we know from our new theorem, the rank nullity theorem, that the rank of a matrix A is equal to the number of pivot columns of A, or the number of pivot columns of an echelon form of A. So looking at our matrix B, which is row equivalent to A, and an echelon form, we see that it has 3 pivot columns, namely columns 1, 3, and 5. So that would be the rank of this matrix. So let's say by the rank theorem, we know that the rank of the matrix A is the number of pivot columns, which we've seen here to be 3. And the nullity of our matrix, or the dimension of the null space of A, is equal to the number of non-pivot columns, which were 2 here. Since we had a total of 5 columns, we know the sum of these 2 values must be 5. We can see that is true here. So now we need to find bases for the column space, row space, and null space of A. So as with our earlier example, by making use of theorem 4.6, a basis for the column space of A would be the columns of A corresponding to the pivot columns that we found in the row-reduced matrix B. So we identified those pivot columns as columns 1, 3, and 5. So our basis, let's call it B1 for that column space, is the set of vectors 1, -2, -3, 3. That is the first column of A. The third column of A, which was 4, -6, -6, 4. And the fifth column, which was 9, -10, -3, 0. All right. Now to get a basis for the row space, we can make use of theorem 4.13 that we started out this section with, which said that the non-zero rows of an echelon form of our matrix forms a basis for its row space. So by theorem 4.13, a basis for the row space of A is the set of non-zero row vectors. So let's call that set B2. And we can see that our first three rows of the matrix B are non-zero rows, so they will form our basis. In this case, the vectors 1, -3, 0, 5, -7, 0, 0, 2, -3, 8, and 0, 0, 0, 0, 5. All right. Now the trickiest part is finding a basis for the null space of A. So here, to find a basis for the null space of A, we have to consider the equation AX is equal to the 0 vector. We want the set of all vectors x which are mapped onto the 0 vector. So this has the same solution set as B times x is equal to 0, where B is our row reduced matrix. So let's consider the corresponding augmented matrix. We have our first row is 1, -3, 0, 5, -7. Second row is 0, 0, 2, -3, 8. Third row is 0, 0, 0, 0, 5. And our last row was a row of all zeros. Now we're augmenting that with the 0 vector, since we're talking about the null space. And in order to determine our solution set, well, we need to take the coefficient matrix B, which is already in echelon form, but rewrite it in reduced row echelon form. So here, to simplify our calculations a little bit, notice that this third row has an entry of 5 in that last column. So we could, of course, take 1/5 of row 3 to make that entry a 1, and then adding multiples of that third row to the first or second row, we can eliminate the -7 and +8 that would appear above that. So this would be row equivalent to the matrix 1, -3, 0, 5, 0. Second row, 0, 0, 2, -3, 0. My third row would be 0, 0, 0, 0, 1, and then I still have my last row consisting of all zeros. And since this was a homogeneous system, our vector on the right-hand side is still the 0 vector. So now this is almost in reduced row echelon form. The only thing that we still need to do is take the leading entry of 2 in our second row and make it a 1, which I can do by dividing my second row through by 2, which would give us the row reduced matrix in reduced echelon form shown here. All right. So now we can read off our solution set, which would be x equals the vector whose 5 entries are given by x1, which using the first row of this augmented matrix we can see is equal to 3x2 minus 5 times x4, where x2 is a free variable. X3, using our second row of the augmented matrix, we can see is equal to 3/2 of x4, where x4 was a free variable. And using our third row of the augmented matrix, we can see that 1x5 is equal to 0, so our last entry for our solution set is 0, which we can rewrite as the free variable x2 times the vector 3, 1, 0, 0, 0, plus x4 times the vector -5, 0, 3/2, 1, 0. All right. So let's give these two vectors a name. Let's call these maybe v1 and v2. And a basis for the null space would be this set of vectors. So here a basis for null A is the set B3, consisting of these two vectors, v1 and v2. All right. Now, one thing that you may want to do, it's not necessary, but we notice that in our second vector, v2, our third entry is a fraction, 3/2. So if we want to consider basis vectors containing only integer entries, well, because x4 is a free variable, I could always double the value of x4 and then eliminate that fraction where I have division by 2. So another vector which we could have used as a basis vector for this null space would be 2 times v2. That is -10, 0, 3, 2, 0. That would have been another valid choice for v2, because every scalar multiple of v2 can certainly be considered a scalar multiple of this original choice for v2. All right. So let's look at some other examples making use of the rank theorem, or the rank nullity theorem. So in this next one, we are asked if A is a 7×9 matrix with a 2-dimensional null space, then what is the rank of A? So let's recall by the rank theorem, the sum of the rank of our matrix A plus its nullity, which is the dimension of the null space of A, has to equal the number of columns of our matrix. So here, the rank of A is what we're after. We're adding the dimension of the null space, which in our problem statement we're told was 2. We had a 2-dimensional null space. And that has to equal n, the number of columns of our matrix. Now this was a 7×9 matrix, so the number of columns n is that second dimension, so 9 here. So solving, we find that rank of our matrix is equal to 7. So the dimension of our column space is 7. So let's consider a similar example, maybe a little more complicated. In part B, we ask, would it be possible for a 6×9 matrix to have a 2-dimensional null space? So let's consider this. If the dimension of the null space were equal to 2 for a 6x9 matrix, we saw, as in part A, that the rank of that matrix would have to be 7. That is, the dimension of the column space is 7. Now, in this example, the matrix that we're working with is a 6x9 matrix. That is, each of the columns of this matrix is only a vector in R6. Therefore, it could have rank or dimension of that column space at most 6. But we saw from the rank theorem that if our dimension of the null space is only 2, then the rank would have to be 7. So here this is not possible. Let's write out our justification in more detail. So no, this is not possible. If a 6x9 matrix, let's give our matrix a name, A, has nullity, or the dimension of the null space of A, equal to 2, then the rank of A has to equal 7 by the rank theorem. However, the columns of A are vectors in R6. Since this was a 6x9 matrix, each column vector only has 6 entries. And so the rank of A, which is the dimension of our column space of A, cannot exceed 6. All right. So let's consider another example. In part C, we are asking if a 6x3 matrix A has rank 3, we need to find the dimension of its null space, the dimension of its row space, and the rank of a transpose. All right. So making use of the rank theorem, or the rank nullity theorem, we know that the sum of the rank of our matrix A plus its nullity, or the dimension of the null space of A, has to equal the number of columns in. So here we were told that our matrix has rank 3. So if we are adding the dimension of the null space of A, or its nullity, we have to get the number of columns, which for a 6x3 matrix is 3. So it follows that the dimension of the null space of this matrix would equal 0. And recall, a 0-dimensional subspace would consist of a single vector, or in this case, the 0 vector would be the only vector which maps to 0 using this matrix A. So we found the nullity, or the dimension of the null space of our matrix. We're also asked to find the dimension of the row space. So here, also making use of the rank theorem, we were guaranteed that the dimension of the row space of A has to equal the dimension of the column space of A, which was the rank of A, which we were given in the problem is 3. So here, directly from the rank nullity theorem, since we know the rank is equal to the dimension of the row space, we have that value as 3. And then in the last part, we're asked to find the rank of A transpose. So here, let's think about this. The rank of A transpose is, by definition, the dimension of the column space of A transpose. Now, A transpose is the matrix we get by interchanging the rows and columns of A. That is, every column becomes a row and vice versa. So the column space of A transpose would be the same as the row space of the original matrix A. So really, the rank of A transpose is the same as the dimension of the row space of A. But we've already shown that the dimension of the row space is equal to the rank, which is 3. So here, the rank of A transpose would also be 3. So in our last part for this example, part D, we are asked if we have a 5x6 matrix A, which has 4 pivot columns, what would be the dimension of the null space of A, or the nullity of that matrix, and is the column space equal to R4? And then justify why or why not. So for this matrix, we were told that we have 4 pivot columns. Now remember that the number of pivot columns is equal to the rank of our matrix. So we can say here the rank of A is equal to 4. And so using the rank nullity theorem, we can determine the dimension of our null space. So let's say by the rank theorem, the dimension of the null space of the matrix can be found by taking the number of its columns, which was 6, and subtracting the rank of A, which was 4. So we have 2 for the dimension of our null space, or the nullity of this matrix. And then we ask the question, is the column space of A equal to R4? Now, in this example, we're working with a 5x6 matrix. So each of the columns of this matrix A is a vector in R5. If we're considering the span of that set of vectors, which would be the column space of our matrix A, it could not be equal to R4 since our column vectors are not vectors in R4. They have dimension 5. So we can say, no, the column space of A is not equal to R4 since the columns of our matrix A are vectors in R5. All right. So this example illustrating some nice applications of the rank nullity.